Great. So it's a great pleasure to have today Stefan Glock, who used to be here in ETH, and now he's in Passau, right? And he will talk about high Hamilton cycles with high discrepancy. Please, Stefan.
Thank you, Benny, and welcome everyone to this talk. So yeah, as Benny said, I'll be talking about tight Hamilton cycles with high discrepancy, and everything I'm going to say today is joint work with Lior Gishboliner, who is at ETH Zürich, and Amedeo Sgueglia, who's at University College London. Okay, so what can you expect from this talk? Well, I will present a new theorem which lies at the intersection of extremal combinatorics and discrepancy theory. I will show you a trick which maybe might be useful to some problem in the future that you're looking at with that deals with the self-avoidance of random walks. I will present a nice structural result on two colored hypergraphs. And in the end, I will present some problems which hopefully you find interesting and maybe start working on them. Okay, so by the way, are the slides moving? Is that okay? Yeah, good. So let me give a kind of gentle introduction to discrepancy theory. So the kind of main basic question is, suppose you are given some structure, can you cut it in some balanced way, or will there always be some discrepancy? So no matter how you cut this structure, there will be some unbalancedness. Okay, so to make this more precise, from a combinatorial point of view, suppose we look at some finite set omega, and we have a family of subsets A of that set omega. And then the question would be, can we partition this ground set omega into two sets such that for every set of our family, we split this set roughly halves. Okay, so you can also think of it as coloring. So give colors red and blue to the elements of omega. And what you want is that for every set A in your family, it has roughly the same number of red and blue elements. And the question somehow is this possible? Okay. And of course, the answer is it depends, right? So a rather easy case would be here if this set family A is rather sparse, or kind of the sets do not have any interference, maybe they're even disjoint, then of course you can just partition each of the sets equally, and you can do this perfectly for all the sets. Okay. On the other hand, if A is very rich in structure, maybe it consists even of all the possible subsets, then of course this is impossible, right? Because no matter which coloring or which partition you take, there will be a gigantic, even monochromatic set. Okay? And the goal of discrepancy theory is somehow to understand the middle ground, right? If you have maybe some rich family A, which is somehow in between these two extreme cases, what can you say about discrepancy? So to formally define the discrepancy, it's kind of convenient to take as colors -1 and +1, because then for any set A, we can just define its discrepancy as the sum of these colors, okay? Because yeah, the same cancels. So the discrepancy of one set is just the absolute value of the sum of these colors. And once we have this, then the discrepancy of the whole set family is defined as follows. For a given coloring, you look at kind of the worst set. Okay, so you look at on all the subsets in your family, and you take the one with the largest discrepancy. This will be the discrepancy of this given coloring, and then you minimize this overall the possible colorings. Okay, so in other words, If the discrepancy of the set family is small, then this means that there exists a good coloring. There is a good coloring C, which kind of splits every set of your family roughly equally. On the other hand, if the discrepancy is large, then that means for every partition, no matter how you make this cut, some set in your family will have high discrepancy. Okay, so what is known in terms of general results? Well, I just present two of the famous results here for general set systems. Here's the theorem of Spencer, who showed that if omega and A both have size n, then the discrepancy is at most 6 times square root n. So this paper is famously called 6 standard deviations suffice. The other theorem I wanted to show here is due to Beck and Fiala, and it has more like a local condition, right? So it doesn't not assume anything about the sizes of omega and A, but what you want is that every element of your ground set omega belongs to few sets. So say at most D sets of the set family, then you also have a bound for the discrepancy, which is here 2D minus 1. Okay, and I should say that discrepancy originated from number theory, I think, but it has been studied also for geometric questions and so on. So the kind of thing is, if you have more information about where your set omega or where your set A comes from, you might be able to prove stronger results. And the kind of perspective that we're taking here is discrepancy of graphs. Okay, so from now on, omega, this ground set, will be the edge set of some graph. So we have some kind of graph structure already on the ground set, and the set family A will correspond to a family of subgraphs. For instance, all subgraphs that are isomorphic to some given graph. Okay? And just to mention two of the classic results in this direction. So Erdős and Spencer looked at the case when this underlying graph is complete and the set family is the set of all cliques. And Erdős, Füredi, Löbel, and Sosch studied the case again when the underlying graph is complete and A is the set of all copies of a given spanning tree. More recently, this topic has seen somewhat of a renewed interest, in particular from the perspective of extremal combinatorics. Okay, so in extremal combinatorics, I mean, one of the basic questions is how many edges does a graph need to have so that you can find a certain substructure. In this talk, we will mainly look for spanning structures. And if you look for spanning structures, then usually you're not asking about the number of edges, but you're asking for minimum degree. Okay, so one of the famous examples of such a theorem is the theorem of Dirac, which says that if you have a graph whose minimum degree is at least n over 2, then this graph will have a Hamilton cycle. Okay, and in this recent paper, Balog, Xaba, Jing, and Pluha, they kind of combined this extremal perspective, like what's the minimum degree you need to find a certain structure, with this discrepancy. Okay? So it's a really nice combination of these two streams of research. And what they could show is the following. So suppose epsilon is some positive constant, and then you choose n sufficiently large. Now, if you have some graph G on n vertices, and its minimum degree is 3/4 plus epsilon times n, then no matter which two coloring you give on the edges of G, right? The edges of G are now this ground set omega. For any partition, any two coloring, you will find a Hamilton cycle with discrepancy at least epsilon n over 32. Okay, so let me just remark here that Of course, this epsilon over 32 is not optimal or anything, but it has the correct order of magnitude, right? A Hamilton cycle has n edges. So if you're asking about the correct order of magnitude for the discrepancy, then this is optimal. One thing you might note here is you have a 3/4. And before I said Dirac tells you that with n over 2, you already get a Hamilton cycle. The question somehow is this threshold 3/4 now optimal, or can you even improve it to n over 2? And the answer is that the 3/4 here is optimal. So let me show you the construction. So basically you start with the complete graph and you fix a set of n over 4 vertices, and then you make them an independent set. So you take out all the edges inside this set, and then your minimum degree drops to 3n over 4. And now I claim there is a 2 coloring for which you will not get a Hamilton cycle of high discrepancy. And as this coloring, we just color all the edges incident with this special set V1 red. So these are all edges going from V1 to the rest of the graph. And all other edges, so which do not touch V1, we color blue. Now, whatever Hamilton cycle you find in this graph, if you look at a vertex in V1, then the Hamilton cycle has to enter this vertex with a red edge and also leave this vertex with a red edge, but all other edges will be blue. So this Hamilton cycle will use exactly n over 2 red edges and n over 2 blue edges, and so the discrepancy is 0. Okay. Now there's also a variation of this problem where you increase the number of colors. Okay, so you can define discrepancy naturally also for more than 2 colors. And there's been some work which determines, again, this minimum degree threshold at which you get starting Hamilton cycles with high discrepancy. So this threshold is 1/2 plus 1 over 2r. If you plug in here r equal to 2, you get the 3/4. But if r is bigger, then this threshold somehow converges to the Dirac threshold. So this was proved by Fresky, Hyde, Lada, Treklown, and independently by Gishboliner, Krivelevich, and Mikhaeli.
How do you measure the discrepancy when you have at least 3 colors?
You basically want more than the average, right? If you have 3 colors, a Hamilton cycle has n edges, so the average is n over 3, and you want 1 color which has more than that.
Okay, thank you.
Good question, thank you. Should say that there has been many further works now on this topic, for instance, looking at oriented graphs, also random graphs. Right here, we have this extremal perspective of having a graph with high minimum degree, but you can also take as host graph random graphs. Instead of Hamilton cycles, you can look for factors. It has been, spanning trees have been considered, powers of Hamilton cycles. Okay, so there has been more work, which unfortunately I cannot all discuss here. But what hasn't been considered was hypergraphs. Okay, so this is kind of what we wanted to initiate with our work to study such problems for hypergraphs. So let me just quickly introduce the notation here. K-uniform hypergraph, which I will always abbreviate to K-graph, is like a graph, but edges do not only have size 2, but size K. Okay, and think of K as some fixed constant, like 3 or 4, something like this. Now, there are different ways to generalize the concept of a cycle to hypergraphs. The one that I'm working here with is that of a tight cycle. So tight cycles are somehow the richest structures, right? Where the most edges have to be there, right? So kind of the concept is you want basically your vertices of the cycle to be in a cyclic order, and then any set of k consecutive vertices on that cyclic ordering should form an edge of your graph. And then, of course, if you want a tight Hamilton cycle, you want this cyclic ordering of the whole set of vertices. And again, any k consecutive vertices have to form an edge. Right, so now it's a natural question to ask, can we find such a tight Hamilton cycle? What are conditions that allow us to do that? So we introduce also some kind of concept of degree. So if we have a set of vertices, then the degree of this set is just the number of edges which contain this set. And then we introduce the minimum such degree, and what we're working with here is the minimum k-1 degree. So there are also other notions of minimum degree. Just to say this here, we look at the k-1 degree. So we consider all the k-1 subsets of our graph and ask what's the minimum number of edges containing such a given k-1 set. Right, and then one of the cornerstones of this type of extremal question is the following theorem of Rödl, Rucinski, and Szemer. So they proved somehow an analog of Dirac's theorem for hypergraphs. It's maybe not the end of the story because it's somehow the threshold for the minimum degree is still approximate, but it's a very nice result. So you fix your uniformity k, you fix a small constant epsilon, and then if the order n is sufficiently large, any n vertex k graph where this kind of minimum k-1 degree is above n/2 plus this epsilon, so 1/2 plus epsilon times n, then you're guaranteed to have a tight Hamilton cycle. So the threshold 1/2 here is optimal, like in Dirac's theorem. For 3 uniform hypergraph, they even wrote another paper determining the threshold exactly, so without this epsilon. And maybe even more important than the result itself is the method which they use, namely the absorbing method. I should say, so I mean, it's often said that they systematically introduced the absorbing method. The kind of main idea of the absorbing method maybe also existed a bit earlier, but they did a very important, achieved a very important milestone of kind of systemizing this method. Yeah, so now I can tell you what our main result is. Our main result is a discrepancy version of this theorem of Rödl, Rucinski, and Szemer, right? So as this earlier result of Balog, Szaba, Jing, and Pluha, who did this for graphs, we now have this result for hypergraphs. And one thing that you might wonder is, well, for graphs, we observed this phenomenon that the threshold for the discrepancy version was actually larger, was 3/4. But somehow surprisingly, we could show that for hypergraphs, the threshold is actually the same. So again, you have a k graph with minimum degree 1/2 plus epsilon times n, and you have any 2 coloring of the edges of this k graph, then there will be a tight Hamilton cycle with high discrepancy. So again, also for hypergraphs, I mean, hypergraphs contain much more edges than graphs, but a Hamilton cycle still has n edges, right? A tight Hamilton cycle has n edges. So this discrepancy here is, again, of the order of magnitude is best possible. Okay, and so I already said that here one of the new observations is that the threshold for discrepancy is actually the same as the usual threshold. Also want to mention that we have the same result also for more than 2 colors. I just stated it for simplicity for 2 colors, but the same holds for any fixed number of colors. And by averaging, we can also get a result for perfect matchings and so-called L cycles. So an L cycle is basically consecutive edges overlap in exactly L vertices. So the tight cycles are basically L cycles when L is equal to k minus 1. What do I mean by averaging here? Well, suppose we have a tight Hamilton cycle of high discrepancy, then the tight Hamilton cycle decomposes into k perfect matchings if n is divisible by k, right? This is a necessary divisibility condition for the existence of a perfect matching. But if you have this, that n divides k, k divides n, sorry, then a tight Hamilton cycle decomposes into k perfect matching, and then by averaging, one of these perfect matchings has to have high discrepancy. I see there's a question.
Yeah. Hi, it's me. I have a question. So is it clear that this mu should be much smaller than epsilon, or is it possible that it's some absolute constant as soon as epsilon is positive?
There might be a better dependence. We didn't try too much to optimize this. Yeah. Yeah, but you're right. In the other result of Balog and others, there was epsilon over 32 here, right? And we have some other constant. Yeah.
Thanks.
Okay. And I should mention that for perfect matchings, this result was proved independently by Balog, Trekloun, and Zarate-Gueren. Okay. Are there any other questions on the result or the general setup? Okay, so if not, then for the remaining time, I'll try to kind of give an overview of the proof of this result. Okay, so here are the kind of main lemmas of the proof of the Rödel-Rucinski-Szemer theorem. And I said before, like a very important aspect of their work was to systemize the absorbing method. And so I thought it's good maybe to also discuss this briefly here and how you can like nicely see how these different lemmas work together to implement this absorbing approach. Okay, so the first lemma which they proved is the so-called connecting lemma, which basically just says that if you have any two k-1 sets, you can connect them by a very short path. Okay, so for graphs, this is kind of trivial. If you have a graph with minimum degree, at least n over 2, then any two vertices have a common neighbor, right? So you have a path of length 2. And you can see this as a kind of generalization of this connectivity for hypergraphs. It's a bit more complicated. You have to work to get this, but you can do it. The second lemma is like the heart of the absorbing approach, the absorbing lemma. What it shows is that there is a special path A. So it's a relatively short path, but it somehow very flexible structure is involved in this path A, so that it has this property that if you add any small set of vertices U, which you can think of as a leftover, then this path A is flexible enough to say rewind itself a little bit and absorb these leftover vertices into the path. So the path A still has the same ends, which is kind of helpful that you're not ruining your overall structure, but somehow it can rewind itself a bit to also incorporate these vertices of U. Okay, so this is the kind of property which you would use in the very end of your proof to kind of finish off. And then there's the path cover lemma, which tells you that there is a collection of vertex disjoint paths which have almost n edges. Okay, so you can think of this as the approximate version, right? A tight Hamilton cycle, like the cyclic ordering, where you have n edges. Now suppose you make some holes into this tight cycle, then what you will get is exactly this collection of vertex disjoint paths that have almost the correct number of edges. Once you have these three lemmas, then basically the proof of the Rödl-Rucinski-Szemer theorem is relatively easy. In the beginning, you take this absorbing path, which exists by the absorbing lemma. To the rest, you apply this path cover lemma, which gives you these vertex disjoint paths. Then you use the connecting lemma to stitch these paths together and also connect them to the absorbing path. And then there might be some really small leftover, but your absorbing path is kind of able to absorb this, and then you're done. I should say that they also have a reservoir lemma, which has this kind of fancy name, but it's basically just taking a random subset and observing that your degrees behave nicely. So this is kind of helpful, this reservoir, that you can use this small reservoir to do the connections. But I mean, this is yeah, this is rather easy. These three lemmas are the main parts.
Stefan, it's also important that this absorber path is very short, so that when you're deleting it, you don't destroy the degrees as well, right?
Yes, it's a relatively short path. Yeah, so when you take it out, the rest of the graph still is a Dirac hypergraph somehow. Yeah. So I'm also kind of hiding the constants here. I haven't told you what this little o here is, but kind of on a high level, these are the ingredients. And so now if we want to prove a discrepancy version of this result, I'm claiming that 2 out of these 3 lemmas we can basically just take as they are, and 1 we have to maybe open up and change. Does anyone want to make a guess which of these 3 lemmas is the one that we have to open up and change? I see one hand.
So probably the path cover, you want to say you can do this while you can get 99% of the edges and like a linear discrepancy.
Exactly. Yep. This is completely correct. So what we would like to have is a path cover lemma with discrepancy. Okay, so we want to have the same result. But additionally, we want that this collection of vertex disjoint paths favors one of the colors. So we have, say, red significantly more often than blue. And then you can just basically do the same steps, use this absorbing connecting lemma to extend this collection to a tight Hamilton cycle. And because the changes that you make in the end to eat up the leftover are so small, you will not ruin the discrepancy anymore. Okay, so this path cover is the kind of main thing we want to achieve. Right, and in the Rödl-Rucinski-Szemer theorem, this path cover is found with the weak hypergraph regularity lemma. So what we do is actually using a different approach here. We use a probabilistic approach based on random walks. So I'm not completely sure. There are many works now around this kind of topics. But I find it interesting maybe here that one can actually avoid the use of the hypergraph regularity lemma, which sometimes people are interested in, well, knowing that you can actually do stuff without the regularity lemma. And what I will do now in the talk is I will first ignore discrepancy and just describe this probabilistic proof of the path cover lemma, and then discuss kind of what you have, where you have to work additionally to get this discrepancy version. Okay. Random walks. To define random walk, as input, we basically we need some kind of weight function x, which gives a non-negative weight to every edge of our given hypergraph. And then we can use this weight function to define transition probabilities of a random walk. So suppose we have some walk, and so far we have visited vertices v1, v2, and so on up to vt. And now we want to say, how do we choose the next vertex? So the next vertex, vt plus 1, because we want to find a tight structure, it has to form an edge with the k minus 1 previous vertices, right? So this is a thing that we need. So we have some set of candidates. The set of candidates for vt plus 1 are all the vertices which form an edge with the previous k minus 1 vertices. And then what we do is we pick this vt plus 1 randomly from this set of candidates, and the individual probabilities are chosen proportional to the x value, so to this weight of the edge that we would use, right? If we choose v, we form an edge with the previous k minus 1 vertices. This edge has a weight, and this distribution that we take here is such that the probability for the next vertex is somehow proportional to the weight of the edge that we would get. Okay, so here in this kind of, intuitively you think of this as a sequence of vertices, but you can also switch to kind of another representation, namely you can think of, well, if you want to formulate it as a Markov chain, then the state space of this Markov chain would be the set of ordered k minus 1 sets, right? So you have a k minus 1 set S, and then you can jump to another k minus 1 set T. Using this formulation, it would be a Markov chain. It will have some stationary distribution pi. And but this is completely, I mean, you can just translate back to the vertex sequence, or the sequence of the ordered k minus 1 sets is it's the same thing. Okay. So now the simple random walk. In the beginning, you have to choose some initial ordered k minus 1 sets, and this we will just do by sampling it from the stationary distribution. And then you start walking according to this rule that I described above. Okay, so now let y1, y2, y3, and so on be the sequence of vertices that we get by following this random walk. Now, this you can define for arbitrary weight functions, but we will actually work with a special type of weight functions. Namely, we want x to be a perfect fractional matching. This means that for every vertex, the overall weight that we get for this vertex, namely if we sum overall edges containing that vertex, sum their weights, then we get 1. Maybe to give a quick example here, this is particularly simple if your graph is regular. So if every vertex has the same degree d, then as your weight function, you can just take 1 over d for all the edges, and you will have a perfect fractional matching. And then you might even be familiar with this fact that, I mean, now you get somehow a uniform walk, right? In each step, you just basically take a random neighbor. And then you might be familiar with this fact that if you have a deregular graph and you just do this random walk by always choosing a random neighbor, what you will get is that this walk behaves uniformly with respect to the vertices. And the same is true here for the hypergraphs, and not only for regular graphs, but also for irregular hypergraphs. As long as this weight function x that you take to define the transition probabilities is a perfect fractional matching, then it will have the property that this random walk behaves uniformly with respect to the vertices. So for each vertex and each time, the probability that your ith vertex of the walk is this vertex v is just 1 over n. So this is kind of a nice property to have, because it kind of tells you that if you run n steps, then you expect each vertex to use or to visit once, right? And ideally, this is what you want in the end. So of course, it's not as simple as this, right? You cannot just take a perfect fractional matching, let the walk run for n steps and get a tight Hamilton cycle. This will not happen. So let me discuss the problems that you have here. So the first problem is that the behavior of this random walk could be quite degenerate if this weight function x is concentrated on few edges, right? So the extreme case would be even that x is just a perfect matching, right? You take a perfect matching, you give weight 1 to the edges in the matching and weight 0 to everything else. Then the behavior which you will get is completely trivial. The first k-1 set will be some subset of one of these matching edges, and then the walk will just go back and forth inside this one edge. So it's completely useless. So I said before that if the graph is regular, you can just take this uniform weighting x, and then all the weights are somehow of the same order of magnitude. And the same is true also for irregular graphs. So there is a tool which already exists. It's a result by myself, Gold, Jos, Kühn, and Ostus, where we proved that you can, in a Dirac hypergraph, you always have this perfect fractional matching, which is normal. So the weights that you give to the edges are of the same kind of order of magnitude. The proof of this lemma is not so complicated. It's based on the switching method. So we use this as a tool for some kind of counting result for tight Hamilton cycles. But here for our problem, we can just use this result. Okay, so we know this first problem we can kind of ignore, or we can solve. The second problem is more substantial, right? We want the walk to be self-avoiding. So we don't want to visit any vertex that we've already seen again. And the conventional approach here would be maybe just to define the walk in this version. So you define a self-avoiding version of the walk, where in each step, the set of candidates is not all the vertices which form an edge with the previous k-1 vertices, but you also only take those which you haven't seen before. And then, of course, you lose the Markov property, you lose all the kind of simple results about being uniform and so on. But it might still be possible to analyze this, actually. So, for instance, one could try analyze this behavior in intervals, and for each interval you try to couple the self-avoiding walk with the simple walk, and if the interval is short, then the kind of total variation distance will not be so large, and so on. But it would be somehow like a very technical analysis. And what I wanted to mention here is a nice trick to basically get around this issue. So what we do instead is we take this very simple random walk and basically just use it to define an auxiliary hypergraph. And then we let the nibble do the rest. So what do I mean by nibble? Nibble is this kind of very general result that if you have an almost regular hypergraph with small codegree, then it has an almost perfect matching. And how can we use this here? Well, suppose we fix some large constant t. We choose capital N to be n to the t minus 1/2. This minus 1/2 is not so important. I will discuss it a bit briefly. And then what we basically just do is we sample n random walks. So we take this random walk model that we have and sample n times. And each time we get a tight path of order t. And then we take this path of order t and add it as a hyperedge to this auxiliary hypergraph. So this auxiliary hypergraph is t uniform, and the hyperedges correspond to the sampled paths. And then because this random walk behaves uniformly with respect to the visited vertices, what we have is that each vertex in this auxiliary hypergraph has the same expected degree, namely n for the number of samples times t times n to the minus 1. And the co-degree of this hypergraph will be at most n to the t minus 2. I should say here, there are a bit, so the one technicality is somehow you want to avoid of getting multiple edges, right? You want to see every t set as a walk only once, and this is why we choose the capital N to be a little bit smaller than n to the t, right? If you choose n to the t minus 1/2, then parallel edges basically don't play a significant role in your analysis, and you can just discard them, okay? And then the nibble, this result of Frankel, Rödel, and Pippinger gives you an almost perfect matching in this auxiliary hypergraph. And this is exactly what we want. It's a vertex disjoint union of paths. And this will have approximately the n edges. So here, this little o of 1 depends on the t, right? The larger you make these paths that you take as your blocks, the smaller the leftover will be in the end. Okay.
So Stefan, so here
Yep.
your t is pretty short, right? Maybe polylogarithmic or something, right?
For us, t being a constant is already enough, but you can probably also take it
But
like
just
slowly.
But in in Dirac graphs, the same approach which people use, that you can work really long doing this self-avoiding. So for
Yeah.
hypergraphs, do you understand this? How long you can work and being still random and self-avoiding?
Yes, I mean, my intuition would be it would run to the end. But this is what I tried to describe here, how you could, in theory, maybe analyze this, but it would be very technical. And what I wanted to mention just is that you can do this short trick of basically getting around this analysis. Okay, so let me now briefly mention what you need to do to get a discrepancy version of this. So one important observation is that for each time and each edge, the probability that we use this specific edge at this time is proportional to this weight of the edge, this x of v. So assume that our fractional or perfect fractional matching x has high discrepancy. So it gives significantly more weight to, say, color red. Then we expect more red edges in the random walk. And this will translate to overall more red edges in this auxiliary hypergraph. And then you would also hope that when you run the nibble, it will produce more red edges in your final path cover. So there you cannot just use this result of Frankel, Rödel, Pippinger, but there is a tool that you can just apply, and this is a result of Ehard, myself, and Jos, a paper called Pseudorandom Hypergraph Matchings, which basically tells you if you want to apply the nibble and you have some statistics, like say number of red edges in your hyper edges, you can still get an almost perfect matching, and these statistics kind of are inherited. So you get exactly kind of the number that you would expect in a kind of heuristic argument. So this thing basically goes through and will give you this path cover with high discrepancy. But what we still need is we just shifted the problem, right? What we want is we want to solve a discrepancy problem. And now I'm telling you, well, if you find a perfect fractional matching X, which has high discrepancy, then you can use all these tools from random walks, nibble, and absorbing to get the tight Hamilton cycle. But we still need to solve this problem about the fractional perfect matching. So basically, we have translated it to a fractional problem. And in the final step, I want to show you how to solve this problem. So suppose you're given some normal perfect fractional matching, which we know that it exists. Can we modify it to get high discrepancy. And a very useful, if you think about this problem, you will see like very useful it would be to find such an alternating grid, right? Suppose you have this grid here, the horizontal edges are red, the vertical edges are blue. Then what you could do is you add positive weight to the red edges and you subtract the same amount of weight from the blue edges. Then for the vertices, nothing changes. So you still have a perfect fractional matching, but you kind of increased the overall weight of red. Unfortunately, this structure does not exist in general, but it would already be enough to find a near alternating grid. So same thing, but we basically don't care about the color of one horizontal and one vertical edge. Then still, and this is the important point here that I want to stress, why the hypergraph behavior is different from the graph behavior. For a graph behavior, if you take this gadget for graphs, you would cancel out, right? But for hypergraphs, you have, even in this near alternating grid, you have at least 2 red edges horizontally, and you have at most 1 red edge vertically. So if you do this weight shifting, you really increase the weight of the red edges. And of course, one such gadget might not be enough, but you would hope that if you can find one such gadget, then you can actually find many edge disjoint such gadgets, and then you would do this kind of weight shifting operation for all these gadgets and thereby significantly change the weight of one of the colors. And so finally, and this is this kind of structural result that I mentioned in the beginning, which is the key tool that allows us to where really you fight for this discrepancy, right? This is the point kind of where you get discrepancy. So we show that your this two-colored K-graph, Dirac hypergraph G, either it has to contain this near alternating grid, or basically it must be almost monochromatic. And in both cases we win, right? If as long as we find a near alternating grid, we can pull them out. And at some point, maybe the second case applies almost monochromatic, but then we just, for the grids, we just push the color that is the monochromatic one, right? And then this color will be the high discrepancy one. Okay, so let me briefly discuss how we prove this key lemma. So in the first step, we do some kind of basic cleaning for every k-1 set and each color. We want that if this k-1 set sees, say, a red edge, then we actually want to know that it has many red edges. And there is a simple standard procedure how you can clean this without losing too many edges. Okay, so this is not the important step, but just that we keep it in mind. If a k-1 set sees a red edge, then actually it sees many red edges. And then we define the k-1 shadow. So shadow is somehow the k-1 sets that are contained in at least one edge. But basically, you can think of this as the complete k-1 graph. The more crucial thing is that we define a coloring for this shadow. And this is done as follows. We look at a k-1 set, which is an edge in this shadow. And if it is contained in a red edge, then we color this set red. And we might also color it blue. If it's also contained in a blue edge, we also color it blue. So the coloring might produce double colored edges. And then there are two cases. First case is that we find many double colored shadow edges. So in this case, because the grid is somehow a partite structure and partite structures have two-run density 0, as soon as you have a few edges which are double colored, you can basically find a grid of double colored edges. And then we basically ignore that these are double colored edges. We just take the color that we want from each edge. And what we can find is an alternating grid in the shadow. Okay, so this is case 1. If you have many double colored shadow edges, you will find an alternating grid in the shadow. And then we extend these shadow edges to proper edges of G, right? We know that each such shadow edge is contained in many edges of this color. So we can kind of build this grid in the graph. And then we use the minimum degree condition to find the two last edges, okay? And there we ignore the colors. We just know these edges exist, but we ignore the color. And we have found our near alternating grid. Okay, and the second case is that we have few double colored shadow edges. And in this case, we want to arrive at the conclusion that the G is essentially monochromatic. So if we have few double colored edges, that means most of the K-1 sets have a unique color. And we want to argue that this unique color is basically the same overall. So what we do is we take two such K-1 sets, T1 and T2, both have a unique color, and we want to argue that this is the same. And here we use a sampling trick. So we take a small random set of vertices, and this small random set of vertices will inherit the degree properties. So you can apply this connecting lemma inside this random sample to find a tight path from T1 to T2. And then once you have this tight path, the color information somehow propagates, right? So assume T1 as a shadow edge is red, then the first edge of this tight path, because T1 is red, this edge has to be a red edge. But then the next shadow edge on the path has to be red as well, because because of the definition of our auxiliary coloring. And then this kind of color of the shadow edges propagates along this tight path to T2. And this will imply that this shadow is almost monochromatic. And this will imply that our graph G itself is almost monochromatic. Okay, so these are kind of the main ideas of the proof. There are a bit more technicalities, some cleaning procedure, but I think these are the kind of main steps. So let me come to the end. So I just want to mention some open problems. So first, we worked here with the K-1 degree, and it would be interesting to study these problems also for other degree variants, for instance, 1 degree or something. Then one could look at other notions of Hamilton cycles. I said in the beginning that our result also implies a version for, say, loose Hamilton cycles, but of course only above this Dirac threshold n/2. But loose Hamilton cycles already exist below this threshold, so it would be interesting to kind of extend the range here. And then it would, well, it seems interesting to study more complex spanning hypergraphs. So instead of just finding a tight cycle, which maybe uses every vertex, but in terms of the edges, it's still kind of a relatively sparse structure. But one could even try to find designs of high discrepancy. For instance, I give you a colored complete 3 uniform hypergraph. Can you find a Steiner triple system of high discrepancy? So in this direction, we have some ongoing work. So this will appear at some point. One can also, so here we looked at minimum degree conditions, but again, one can look at the random model, study random hypergraphs. And finally, I want to mention a very specific problem, which goes back to the original definition of discrepancy. And basically the question is, how robust is discrepancy? So suppose like this very general setup, you have omega as a set, you have A as a family, and now you take a random subset of omega. So even just keep every element of omega independently with probability 1/2. And you look at the induced family. So all the sets that are still subsets of this random subset. Can we say anything about the discrepancy of A prime? So suppose A had high discrepancy. Can we get any kind of sensible lower bound on the discrepancy of A prime? This seems interesting. So thank you all for listening, and I'm happy to take any questions.
Yes, thank you, Stefan, for a nice talk. So let's give Stefan a round of applause. Actually, I have a question about exactly the last thing. So if you sampling thing with probability half, can you get some information, because you kind of will have a family and its complement, right? And maybe so why something like that would not say anything, right? So you take your this random subset, you intersect it with the family, you got some family, and then you take a complement. Imagine they both have low discrepancy. Then you can glue these colorings to get a low discrepancy for the whole, right? Because every set is just now two pieces.
But so when I said induced, I didn't mean that A prime, I shrink the sets, right? I just really, I keep only the sets which are entirely contained.
So you're not taking an intersection, you're just taking, okay,
Yeah.
Now.
So I think, so the more interesting maybe case here is not that the probability is 1/2, but rather something small. So I want to think, I think maybe one can come up with really strange families where maybe you can't say much, but there should be some kind of conditions that you can impose which make this a very good question. For instance, using this recent breakthroughs on the expectations threshold conjecture, right? So you might think of omega again as the edges of some graph, and A is the set of Hamilton cycles. Now this random sample is again like you take G and P, and you want to understand the discrepancy of Hamilton cycles in random graphs, right? And maybe if say A is spread, then you can say something about the discrepancy. So this is kind of the direction which
I understand. But important is it's the sets which are completely contained in.
Yes. But I mean, you can change the question, right? I mean, you can also take the intersections and study this.
More questions, please.
So, hi, thanks for the talk. I wanted to ask a very vague question, so I'm sorry if it makes no sense, but about these perfect matchings, is there any connection between them and these spread measures, maybe on matchings, and also the behavior of random walks and spread measures?
Sorry, I don't exactly get the
just if it makes no sense, it's okay. It's just that the definition itself, because you're bounding the weight of a specific edge, it reminded me of the definition of a spread measure. That's all.
Yes, I mean, so what's recent? It's a big topic recently. I mean, we have this breakthrough on the threshold, expectation threshold, but it's not so easy to actually show that, say, Steiner triple systems are spread, right? And then there are these papers which kind of have these small augmentations to show that you can actually design a spread measure. If this is kind of the direction that you wanted to ask.
Yeah.
Yeah, I mean, on this high level, then yes, but I'm afraid I don't have anything more concrete.
More questions? If not, let's thank Stefan again. Right, thank you, Stefan.
Thank you all.
We can stop recording.